Hey everyone, we are now doing vector application, so actual real life ways that we can see vectors. There are a couple of things at the very beginning we're going to go through just to make sure that we understand before we actually get to working through some of these problems. So just real quick from the picture that we have on this first slide, it says two forces can act together or against each other. Either way, one of the forces will have a definite effect when combined with another force. So our vector is going to represent a force that's being applied. So here we go. Some things that we need to know. You need to know direction angles and bearings. Now, we've talked a lot about direction angles. That's from the positive x-axis over and around. Bearings are always your directional values that are off of your y-axis, so they're coming from due north, okay? So there's a little bit of a difference for those. The first one, just to get ourselves situated with this, is 40 degrees south of west, okay? So follow the directions that it says south of west. So that means I need to travel west and then go south. Okay, so if I go south of west, my 40 degrees is going to occur at right on the x-axis near the origin. Okay, so this is actually a direction angle because that's coming from the positive x-axis over. Okay, the next one is south 40 degrees west. Okay, this one tells me to go south first 40 degrees and then go west. So south 40 degrees and then west. This 40 degrees is coming off of the y-axis, so it is a bearing. All right, so do you notice the difference between the notation? If it's a direction angle, you get the angle first. If it's a bearing, you get north or south first, then your angle, okay? The one in the bottom left corner, a bearing of 40 degrees, that can be off of the y-axis, northeast, southeast, northwest, or southwest. So if I go northeast 40 degrees, or if I go southeast 40 degrees, southwest 40 degrees, and northwest 40 degrees. Excuse that testing while we're going through. Sorry about that. The last one, due north, like that's a piece of cake, right? Yeah, we get due north. Start at the origin, go straight up. That is always going to give you a 90-degree angle every single time. Don't got to worry about that one. Pretty easy. Okay. All right. Out of the west. Okay. So what does that mean? Yep, that's exactly right. It means you start in the west and you come out of it, or you move out of the west. So you are actually traveling eastwardly, or traveling east. Okay, you're going east. Our next one, ground speed. That just means that you are on the horizontal. Doesn't necessarily matter the direction. Like you don't have a negative speed, you're just going a different direction. So this is on the horizontal. And let's see, a turn of 40 degrees. Okay, so remember our turn angles. I think it's a little easier if we just kind of follow. So if I'm starting at the origin and I'm traveling to the right, I'm going east. Okay, if I turn 40 degrees, it doesn't matter which way I turn. If I turn and go this direction, excuse me, from that second point where I am, if I turn and go up and to the right, so if I turn northeast, then my turn angle happens, where does that happen? That's right, it's on the outside because I would be continuing to travel eastwardly. So there's the turn of 40 degrees and its supplement 140 degrees would be on the inside if I were to like create a triangle from two different vectors or something. Okay, so Again, if I'm traveling a certain way, doesn't matter. So this time I'm traveling north. I turn a particular direction. My 40 degrees happens on the outside, and then its supplement 140 would be on the inside if I were creating a triangle. And then some things to remember just about parallelograms and their angles. So we know that opposite sides of parallelograms are parallel. They are also congruent, which means that your opposite angles are going to be congruent. So angle A is going to be congruent to C, and angle B would be congruent to D. And then the other thing to note is that the same side angles are going to be supplementary. They have a sum of 180 degrees. Okay, there you go. So just some things to remember as we're going through this particular lesson. And we're already 5 or 6 minutes in, so we're only going to do a smidge at a time for these. Like, we're going to take it piece by piece. Okay, random example. Imagine 2 people are pulling on your arms. Why? I don't know. Just imagine it. Okay. The first person is pulling in a northerly direction with the same force as the second person. So both of them are pulling you in a northerly direction. Okay, what's going to happen? That's exactly right. You are going to travel in a northerly direction. Now, it's going to be, instead of one person doing it, because 2 are doing it, it'll be double the amount of force, so twice the force. Okay. All right, the second one, what if one person pulls towards the north and another pulls towards the south with the same force? Well, in that case, until someone pulls stronger, they're going to really not do anything. You're not going to change direction because they have that same force opposite directions. Okay. And then our last example, what if the person pulling towards the north is stronger than the person pulling towards the north? Well, then of course, in that case, you are going to end up moving more towards the north direction than the south direction. You're going to move in a northerly direction. Okay, I think we got all that down pat. Now we can actually talk about some examples. All right, so example 1, we have a gun which has a muzzle velocity, so the part of the gun that the bullet comes out of, muzzle velocity of 1,200 feet per second, and it's fired at an angle of 6 degrees with the horizontal. Determine the horizontal and vertical components of the velocity. So our vector is represented with velocity in this case. So we're talking about the velocity of that bullet coming out of the muzzle. Okay, so think about what we have. We have an angle at 6 degrees, and we have a velocity, which is our magnitude of our vector, traveling out into quadrant 1, which has a velocity of 1,200. So basically the hypotenuse is 1,200, and you have an angle of 6 degrees. You're determining the horizontal x and the vertical y components to see how fast horizontally and vertically it travels, that bullet travels individually. Okay, we did problems like these already. You just have to make sense of the word problem and then draw your picture of things you've already done. So we do have ratios of sine and cosine to solve for y and x. Our horizontal is x. So we will do adjacent over hypotenuse equals cosine of the angle. So x over 1,200 is cosine of 6 degrees. Cross multiply, x will be 1,200 multiplied by 6, which is 1,193.4, and that would be feet per second. Okay, vertically, so we're looking for the y. That's going to be our opposite side over hypotenuse. So sine of 6 is y over 1,200. Cross multiply, and y equals 1,200 multiplied by sine of 6, which is 125.4, again, feet per second. So horizontally and vertically, you have 1,193.4 feet per second, and vertically it's 125.4 feet per second. And then you could also write that in component form with those horizontal and vertical components. Okay, that was our first one. I'm going to do my best to get through as much of the second example as possible. We might have to split it into 2 videos because we're at 9.5 minutes already. All right, here we go. For number 2, we have 2 draft horses, my absolute favorite. I love Clydesdales. Oh my goodness, they're so awesome. They are pulling on a tree stump that has forces of 200 pounds and 300 pounds. The angle between the forces is 65 degrees. Okay, determine the magnitude of the resultant force. So we are not going to worry about these little lines that we already have on our graph over here in our picture. We're just going to fiddle with them later. Okay, we don't have, like we have the angle between the 2 forces, and we've got a tree stump. Okay, so let's start with that. So here's a tree stump, and I've got one horse that's pulling at 200 pounds, and another horse that's pulling at 300 pounds of force, and the angle between those 2 horses pulling that tree stump is 65 degrees. Okay, so how in the world can we separate that out so that we can actually get 2 different vectors so we can add them to determine their resultant force? Okay, so like keep life simple, guys. Really keep it simple. Go ahead and make one of the vectors be on the horizontal. Okay, so the first one, I'm going to put that on a horizontal. So I just want that to be as easy as I can have a vector. Okay, so if I start at 0, 0 and I go to the right 200, that's my vector. And it would have a component form of 200, 0, because I'm only traveling horizontally. That one horse is just going straight across the ground, okay? So we're basing everything off of that first horse. The second horse we're going to draw with a 300-pound force going at that 65-degree angle from the first horse. Okay, so it's going to go in quadrant 1 at a 65-degree angle, has a magnitude or a force being pulled of 300 pounds of pressure. Okay, so in this case, I got my first horse done. For my second horse, I need to determine horizontal and vertical components. Okay, that way I know component form of the second vector. So we just did that in the last problem. Let's do that off to the side. So our horizontal, our x value, that's going to be adjacent over hypotenuse. So cosine of 65 equals x over 300. X will equal 300. Oh, excuse me. Yeah, that's right. 300 times cosine of 65 degrees. And our horizontal component is going to be 126.8. Okay, so I already know horizontal component, 126.8. Awesome, yay me. Now to get the vertical component, just like we did in the previous example, that's the opposite side of the angle over hypotenuse. So sine of 65 is, y over 300. Okay. And then cross multiply. Y equals 300 multiplied by cosine. Oops, nope. Sine of 65. Silly mistakes. Be careful of that kind of stuff. We all do it. So then our y component is 271.9. So vertically, it's 271.9. All right, cool. We got component form. So now the resultant. Well, how do we get the resultant? We take the first horse, its component form of its vector, and the second horse, and we add them together. Okay, so resultant. That's going to be 200, 0 plus 126.8, 271.9. So our resultant is going to have component form of 326.8, 271.9. Okay, that is only the resultant. What does it ask us to do? Yep, that's exactly right. It asks us to determine the magnitude of the resultant force. Okay, so to find the magnitude, I'm just going to make this R. So the magnitude of R for the resultant is going to be the square root of 326.8 squared plus 271.9 squared. And when you type that into your calculator and simplify, you get 425.1. Okay, what again does that represent? Pounds of pressure at which it's pulling. Okay, so the resultant of the two horses pulling together is 425.1 pounds. There you go. Good job. All right, we did it. We sure did. Let's see if we can go ahead and finish the second part of this guy, because we're still going to use that same info. Okay, so what's the angle between the resultant vector and the 300-pound force? Okay, think about what that means. So we had the original horse with the 200 pounds of pressure here, and then we had the second, so first and second horse, that was 300, okay? So however you choose to add, it doesn't matter, but the angle between those two is 65 degrees. So what they're wanting to know is the resultant force. Well, our resultant force, if I were to add however you want to do it, that would be plus your 300. So here's my resultant force. I'm sketching that guy in purple. It has component form. Don't forget, we just did it, 326.8 comma 271.9. And we know it's magnitude, but we don't need that part. We know that the entire angle between the two vectors is 65 degrees. Okay, so we want to know what is it between the resultant and the 300-pound horse, just that little piece. So we're going to use component form of the resultant and find an angle measure. Cool, we got that. So theta, that's going to be tangent inverse of the y over the x, the sine over the cosine, or the b over the a, however you would like to think about that. 326.8, there you go. So tangent inverse of 271.9, that vertical component, divided by horizontal component, 326.8. That actually gives us 40 degrees. So theta is 40 degrees. Okay, so the difference between those two is 25 degrees. Yep, so we had to do the 65 minus the 40 to help us determine the 25 degrees between the resultant and the 300 pounds. So it's 40 degrees in between the first horse that was on the horizontal and the resultant force. Okay, great job. That's a little over what we like to do, but that's okay. We got 2 of them done, and we'll come back in another video for the remaining problems of this set.